Hey, welcome back. So today I'm going to go through and see if I can do a whole bunch of videos all at once. Silence everything. Okay, put everything on mute so hopefully we don't get disturbed. Anyway, yeah, so I'm going to go ahead and try to record a whole bunch of videos. I have 2 lectures for the week that we need to get done. I want to post like an extra video. Tonight I'm going to try to do a MATLAB at midnight if I can, relating back to linear differential equations. And so just trying to punch all these out. I also have a talk I'm giving in a week. If any of my students are curious, I can send you a link to it. But yeah. So I have just a couple hours to try to get everything done. So we'll see how that works out. So today we're moving into chapter 4, and I believe we're starting on section 4.2, but we'll double check when we get into the lecture itself. So the idea of the lecture is we're going to be talking about these second order linear differential equations, and for the first chunk of this chapter we're talking about these same things with constant coefficients. Later on we'll get into a little bit more with non-constant coefficients, I think, if we have time. No guarantees. I might post a video about it anyway, but might not make it part of the exam, but we'll see, so don't hold me to that. In any case, so we have the second order linear differential equations with constant coefficients, and the first 2 sections here are going to be what we call homogeneous equations, or homogeneous equations, where basically there's not going to be any sort of functions of t floating around on the right hand side. So what does this mean? Well, that means that we can take advantage of some nice algebraic properties, and we're going to be going back and learning how to factor polynomials. For the most part, we're just sticking in second order equations, but I think the homework goes into a couple of third order equations, maybe a fourth order equation here and there, just to give you an example how you can extend the method. But the general technique is very simple. So you make a guess, and the guess is that you just guess that you're going to have y is equal to e to the rt. Now, why do you do this? Well, the idea is that the second derivative, the first derivative, and the function itself should all be able to cancel with the right kind of coefficients. And that's what you're going to see in the differential equation, because basically they should cancel because it's equal to 0. And so if that's going to happen, then that means that when you take derivatives, you should be able to get roughly the same kind of function back. And so, and we know that's certainly going to happen with a function like e to the t or e to the rt, but you don't know what r is. So when you go through and you actually plug this in, or you plug in y, the first derivative is just going to be r times e to the rt, and the second derivative is r squared times e to the rt. So the second derivative, the first derivative, and the function itself all share e to the rt. And what does that mean? Well, that means you can factor it out. And what you're left with is you have what we call the characteristic equation, or the auxiliary equation, and that is equal to 0. We know that's equal to 0 because e to the rt can't be 0, and so if you have e to the rt times a polynomial and that's equal to 0, then that meant the polynomial is 0. And now you have a way of finding r. You have a polynomial equal to 0, and now you can use all those tools from pre-calculus, college algebra, algebra 2, algebra, in order to find the zeros of that polynomial. And once you do, you can plug those back in. You could, for a second order differential equation, you're usually going to find 2. And you can plug each one of those into e to the rt, and each one will give you a separate solution to the homogeneous equation. The general solution is going to be c times e to the r1t plus c2 times e to the r2t. Now, it can happen that you have a repeated root. So you have, say, r naught, and so it's like r minus r naught squared could be the solution. And then that means that you're going to have 2 solutions of this form, where you're going to have e to the r naught t and t e to the r naught t. And then when you want the general solution to that differential equation, it's going to be c1 e to the r naught t plus c2 times t e to the r naught t. And that's the whole section. Here we're not going to be talking about anything that's going to be giving us complex roots. That's going to be the next section. When you add in complex roots, that actually kicks out the possibility of having sines and cosines. But for the first section, we're just going through and just doing it with real zeros and real roots. And yeah, I just explained to you the entire thing. So if you felt like you got it, check out, go do the homework and make sure you understood. And otherwise, hang in there and we'll go do a whole bunch of examples in lecture. All right, let's get into it.
Okay, so let's go ahead and get started. So here we're taking a look, and this is section 4.2 out of Nagle, Saff, and Snider. Their book, Fundamentals of Differential Equations. This 9th edition. Okay, and so what is this section? This section, we're going to be talking about homogeneous linear equations. Usually they're going to be second order. Sometimes it might be first order, and occasionally we might talk about higher order, like third or fourth. But okay, so what is the general idea? So for a linear differential equation, we're going to have, with constant coefficients, we're going to have something like this. So we're going to have a times, say, dy by dx, let's make the second derivative, plus b, well actually, instead of x even, let's keep it to t. I think most of these examples are dy dt. Plus dy dt, plus c times y is equal to f of t. This is the general, this is the linear differential equation. This is second order, and it has constant coefficients. Okay. So it turns out that in order to find a solution to this, it's going to be a little bit more involved, and we're going to have to invoke something called a superposition principle to get a general solution. What we're going to be covering for now is, instead of having this f of t, we're going to replace f, we're going to put 0 here, and this is what gives us what's called a homogeneous equation. I often say homogeneous, but I think homogeneous is technically what it is. And so we're looking for ways of solving this differential equation for now in section 4.2. We'll get back to the other ones later. So section 4.2 and 4.3 are completely focused on this. And what we're going to do is we're going to try to find some way to make everything here on the left cancel out and give us 0. Well, if we're going to do that, then that means that y and dy dt and the second derivative of y must all have roughly the same form, so they can kill each other or annihilate each other, or whatever nice euphemism you'd like to use. So how can we come about this? Well, we know, for instance, we're going to make a guess, and our guess is going to be just that y of t is equal to e to the rt. We don't know what r is, but let's go ahead and assume that this is the form we have. What's nice is that if I take a look at y prime of t, I get r times e to the rt, and if I take a look at y double prime of t, then I just get r squared e to the rt. And so then, these are all functions that are basically exponentials, plus some constants out front. R is a constant. We don't know what it is, but that's what we're getting. So what we can do then is we can go ahead and plug all these in, and this is what we get. We get a times r squared times e to the rt, plus b times r times e to the rt, plus c times e to the rt is equal to 0. If y was the solution, that would mean that it's equal to 0, and this is the second derivative, this is the first derivative, this is the 0th derivative, or the function itself. And then what we can do is we can notice that all of them have e to the rt in them, and so we can factor it out. So we get e to the rt times a times r squared plus br plus c is equal to 0, and so then that tells us that r must satisfy this. ar squared plus br plus c is equal to 0. You can obviously extend this to third dimension, and then instead of getting r squared here, you get r cubed. But as long as we just are talking about second order equations, we can always figure out r is pretty quickly, and that's through the quadratic equation. So that tells us that r is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and so there we go. This is, clean that up, there we go. All right, so this is the quadratic equation, and it can be used to solve our problem. Now, we know that if this ends up being negative, we're going to end up kicking out an imaginary number out of the square root, and that gives us complex roots. For today, we're just going to be making the assumption that this is always going to be positive, and so we're going to get real roots out of it. Okay, so what does that say? Well, basically, it tells us that if, say, we have two distinct roots, then what do we get? We get y is equal to, say, e to the r1t, and y1, let's say, and y2 would be e to the r2t. So we end up getting two different solutions out of this. And these are what we call, these are linearly independent solutions if you can't just scale one and to get the other. So, so in this case, we can actually come up with a whole family of solutions, and this leads to our general solution, where basically we take linear combinations of these. So y being, say, c1 e to the r1t plus c2 e to the r2t, right? And so this is our general solution. And if we have one repeated root, then what do we get? We get y is equal to, say y1 is equal to e to the, say, r naught t, and then we get y2 is equal to t times e to the r naught t. All right, so this is going to be the other form we get. So your general solution then is going to be y is equal to c1 times e to the r naught t plus c2 times t times e to the r naught t. All right, so that's generally what you're going to get. Okay, and so this is basically the entire lecture. And the rest is just a matter of figuring out little details. Okay, so let's go on and actually do an example. So example 1, they want us to find a pair of solutions to y double prime plus 5y prime plus 6y is equal to 0. Oh, that wasn't a plus, that was a minus. Okay, so let's go ahead and do it. So again, we're going to go ahead and make the assumption, or we're going to make the guess, rather, that we're going to have y of t is equal to e to the rt, and figure out what r must be. Okay, so let's go ahead and do that. Okay, if I plug everything in, just like it before, we're going to get, say, we're going to have that y prime is equal to r times e to the rt, and we're going to have y double prime is equal to r squared times e to the rt. And if I put both of these in, I'm going to get this. I'm going to get, say, r squared e to the rt plus 5 times r times e to the rt minus 6 times e to the rt is equal to 0. Right? And so then that tells me if I factor out e to the rt, I get r squared plus 5r minus 6 is equal to 0. And finally, that tells me that r squared plus 5r minus 6 is equal to 0. We know that the polynomial must be 0 because this is never 0. Okay. So now let's go ahead and factor that. So then that tells us that we have r, do it nice, r, let's see, I think it's plus 6 r minus 1 is equal to 0. I think that's how we'd factor it. Because we know we can factor 6 into 6, negative 6 times 6 minus 1. And then if we multiply these back together, we're going to have a 6r minus 1r, and that gives us a 5. Right, so, okay, there we go. So what does that tell us? Well, it tells us that we have the roots of not 6 and negative 1, but rather negative 6 and 1. So if r is equal to negative 6, that makes this 0. And if r is equal to 1, that makes this 0. Okay, so now we plug those values in, and we get two solutions. We get y1 of t is equal to e to the minus 6t, and we get y2 of t is equal to e to the t. And there we go. So that is our pair of solutions to the differential equation. Okay, cool. So, let's see another one. All right. Here, actually, they're just asking us to solve the initial value problem. Example 2. So it's to solve the IVP, where we're given y double prime plus 2y prime minus y is equal to 0. They tell us that y of 0 is equal to 0, and they tell us that y prime of 0 is equal to negative 1. Okay, so let's go ahead and do it. So again, we're making the guess that y is equal to e to the rt. And then that tells us that we're going to get this auxiliary equation of r squared plus 2r minus, minus 1 is equal to 0. So then what we can do is we can go ahead and factor that, and that's going to give us, say, r minus 1 squared is equal to 0. Maybe. I don't think so. Let's see, what else could I give us? So yeah. All right, so I'm going to have to use a quadratic equation. So we get r is equal to negative 2 plus or minus the square root of 4 minus 4ac. So it's going to be plus 4 divided by 2a. So that gives me negative 1 plus or minus the square root of 8 over 2. And well, the square root of 8 is 2 root 2, and so that gives me negative 1 plus or minus the square root of 2. All right, that is not something I would have been able to guess. Okay. So that gives me two solutions. It gives me y1 is equal to, say, e to the minus 1 plus or minus, plus square root of 2 times t, and it gives me y2 is equal to e to the negative 1 minus root 2 times t. Okay, so my general solution then is y is equal to, say, c1 e to the negative 1 plus root 2 t and plus c2 times e to the negative 1 minus root 2 times t. Okay, so now we want to solve the initial value problem. Well, we have two unknowns that we need to resolve, and we can do that by using these initial values here. So, first of all, we know that y of 0 should be equal to 0. Well, a y of 0 is actually equal to c1 plus c2, because if I put zeros here and here, we just get 1 out of the exponential. Okay, and let's see, so we need y prime. So y prime of t, I have to figure out y prime of t before we figure out y prime of 0. We get c1 times 1 plus root 2 times e to the negative 1 plus root 2 t plus c2 times negative 1 minus root 2 times e to the negative 1 plus, or minus root 2 t. Put in 0 for t in both of those, and what do we get? So we get y of 0 is equal to, well, we know it should be equal to negative 1 from the initial value up here. And what we get otherwise is c1 times 1 plus square root of 2 plus c2 times negative 1 minus root 2. The exponential sort of vanished because if you plug in e, if you have e to the 0, you just get 1. Okay, so now we need to solve for c1 and c2. Well, there's a lot of ways to do this, but one way we can do it is we can just go ahead and use substitution. So this guy tells me that c1 is equal to negative c2. And so then I can plug it in here. I get negative 1 is equal to, say, negative c2 times 1 plus root 2 plus c2 times negative 1 minus root 2. Okay, so I think what we're going to get then, Oops, and that should be a -1 there, -1 there. My mistake, sorry. -1 there. Okay, so what do we get? Well, negative C2 times -1 plus C2 times -1 is going to make those annihilate. And so what we're going to end up having is a -2 C2 when you work everything out. Yeah. And so then that tells us that C2 must be equal to 1 over 2√2, or 1 over √8 if you like. Okay, but that tells us then that C1 is equal to the opposite of that. All right, so that tells us that the solution to the initial value problem is what we get when we plug in C1 and C2 into that equation. So we get y of t is equal to, C1 is -1 over 2√2 times e to the -1 plus √2 times t, plus 1 over 2√2 of e to the -1 minus √2 of t. And there we go. So this is the solution to the initial value problem right here. Okay, not too bad. Okay. So there's a handful of things that the book really wants to talk about here. And one of them is the linear independence. Idea. And so the idea is, when we're asking for two linearly independent solutions for the differential equation, this is something that we're going to be trying to keep in mind. For instance, if I were to write y1 of t is equal to, say, e to the t, and I say y2 of t is equal to 2e to the t, these aren't what we would call linearly independent. And the reason why is that if I take 2y1 and I subtract y2, you end up getting 0. They're kind of the same function in that way. And so, so what we're looking for is basically a pair of functions say y1 and y2 is said to be linearly independent over the interval I if and only if neither of them are constant multiples of the other. Okay. And otherwise we say they're linearly dependent. Okay. So this was an example where we had linear dependence. Linearly independent solutions would be, say, earlier when I was talking about repeated roots, for instance, we had like e to the r naught t, and then we had r2 of t, which is t times e to the r naught t. And this is for repeated roots. So these are linearly independent. And y1 of t is equal to, say, e to the r1t, and y2 of t being e to the r2t for r1 not equal to r2 is linearly independent. Right? And so when we're looking for solutions to this differential equations, we are looking for a second order differential equation, we are looking for generally two linearly independent solutions. Okay, so what does this matter? Okay, so here's a little technical bit. So if we have the existence and if you take a look at the existence and uniqueness theorem that they gave us here, basically it says that for any real number A, numbers A, we're going to assume A is not 0, B, C, T naught for initial value, Y naught for another initial value, Y1 for another initial value. I'm going to put fancy math speak. There exists a unique solution to the initial value problem. So we'll call a star, where we have AY double prime plus BY prime plus CY is equal to 0, where we take Y of T naught is equal to Y naught, and Y of T naught prime, Y prime of T naught is equal to Y1, and the solution is valid over, say, negative infinity to infinity. Okay, so what does this matter? Well, basically, if we have so basically we have another theorem in here. If y1 and y2 are linearly independent solutions to a y double prime plus b y prime plus c y is equal to 0, then the solution above can be written as y is equal to c1 y1 plus c2 y2. Sorry to cram everything in there, but that's the idea. So basically, once we find two linearly independent solutions to our differential equation, we can take any initial value problem and write the solution in this form. So that procedure that we just did, where I went and I found two independent solutions, linearly independent solutions, said the general solution is written this way in terms of C1 and C2, and finding C1 and C2, which gave me this, that is basically, that will always work for finding a solution to the initial value problem. And so that's really nice. Okay, so let's take a look at the next example. So example 3. We want to find a solution to the initial value problem, where we're given y double prime plus 4y prime plus 4y is equal to 0. And we're told that y of 0 is equal to 1 and y prime of 0 is equal to 3. Okay, so again, if we make this guess to find our two linearly independent solutions, I'm going to have y of t is equal to e to the rt again, and that's going to give me this auxiliary equation. So where it's going to be, say, r squared plus 4r plus 4 is equal to 0. And then, of course, we can factor this, and it's going to be r plus 2 squared is equal to 0. So here we're in the case where we have a repeated root. That tells us we're going to have two solutions. We're going to have y1 of t is equal to, say, e to the negative 2t, And then y2 of t, because we have this repeated root, and I was telling you this, is get t times e to the minus 2t. All right, those are our two solutions. So now we know that from the theorem I just told you, the solution to the initial value problem, we can write it like this. So y of t is equal to, say, c1 times e to the negative 2t plus c2 times e to the negative 2t, but then we had a t here. All right, now if I go ahead and set equals 0, we can get one of the coefficients right away. So if I set equals 0, I get c1 times 1 plus c2 times 0, because we have this t here. Well, then that tells me, since we know by the initial value problem this should be equal to 1, that tells me then that c1 is actually equal to 1. Okay, well, that makes life a little bit simpler. Now let's go ahead and take the first derivative. So we have y prime of t, and this way we can fit the other initial value. So we get negative 2 times c1 e to the negative 2t plus c2 times e to the minus 2t plus negative 2 times t times e to the negative 2t. Okay. Now we know what c1 is already, and if I plug in 0 into this equation, I get 3 from the initial value that we're given, and then otherwise I get negative 2, c1 is 1, so I'll just leave that, and e to the negative 2t is just 1, so I'll leave that alone too, plus c2 times, looks like 1 minus 2 times 0, right? And so that tells me then that we have 3 is equal to negative 2 plus c2. And then that tells me that c2 is equal to 5. Okay, now I can go ahead and plug those back in, and I get y of t is equal to, say, e to the negative 2t, because c1 is 1, plus c2 being 5, gives me 5 times t e to the negative 2t. Okay, there we go. And now we've solved that initial value problem. Okay, one more example out of this section, and then we're done. Sorry if you hear babies yelling in the background. That is my household. So he wants to find a general solution to y triple prime plus 3y double prime minus y prime plus 3y is equal to 0. So this one is actually a third dimensional equation. And again, all we need to do is use that guess of y of t is equal to, say, e to the rt. Okay, so the only thing that changes here is we're going to kick out an r cubed here. And so that leads to auxiliary equation of r cubed plus 3r squared minus r plus 3 is equal to 0. Now you might ask, how in the world do you find a solution to this? Well, it's actually not too bad. If you're going to have any luck of finding anything, this is a monic equation, so we don't have anything in front here. So the rest would really just be factors of the last term. So things to try are, say, r is equal to plus or minus 1 or plus or minus 3. That's all we can do. If I put in r is equal to 1, what do we get? Well, we get 1 plus 3 minus 1, sorry about my babies, and then we get plus 3, and that's not equal to 0. Okay, what about r is equal to negative 1? What do we get? Well, I get, say, negative 1 here, plus 3, plus 1, and plus 3, if I did it all right. Yes, and that is, again, not equal to 0. Okay, so r is equal to 3. Let's see. Something better work eventually. Let's see, so I get 27 plus 3 times 9, which is, again, 27, minus 3 plus 3, and that's, again, not equal to 0. So now we get r is equal to negative 3. I swear this should work. So we get negative 27 plus 3 times 9 again, that's 27. Okay, good. And I get negative 3, so I get plus 3. Did I copy that down right? I did not. Oh my goodness. Shh. So the takeaway here is that you want to write the equation correctly. Minus sign. Minus sign. Oh my goodness. Now it's actually going to end up working. All right, so now if I put in 1, I was like, I remember this working out better than that. So we get put R1, then we get 1 plus 3 minus 1 minus 3. That's 0, so that says that R equals 1 is the root. I can try R is equal to, say, negative 1. Let's see what happens. I get negative 1 plus 3 plus 1 minus 3. And again, that's equals 0. So that tells me R equals negative 1 is also a root. And then I get R, let's try 3? Negative 3. Let's try negative 3. Let's see. We get negative 27. We get plus 27. We get plus 3. We get minus 3. And that's equals 0. So that tells us that R is equal to negative 3 is a root. If you like, then that tells you that this is written as R plus 3, R minus 1, R plus 1. And we can factor it that way because it's monic. And on the other hand, we didn't have to write that because we already have the roots. So once we have the roots, we can write 3 linearly independent solutions. This is a cubic, so then we want 3 linearly independent solutions. So we get e to the minus 3t. We get, for 1, we get R2 of t could be, say, e to the t, and R3 of t is equal to e to the minus t. And putting them all together, the general solution is y of t is equal to c1 times e to the minus 3t plus c2 times e to the t plus c3 times e to the minus t. And there we go. We're done. And so now we'll just cut back to my outro.
Okay, so yeah, that was it. Not really too complicated. The whole idea is that we're going to be pulling out a polynomial each time, find the root set of polynomial, and that feeds into e to the rt, which is the solution. So the general solution is where we take what we call a linear combination of these. And the reason why we can do that is because it's a linear equation. And so later on, we're actually going to leverage this idea of being able to take linear combinations and putting them back together. And that's actually what's going to give us the sines and cosines out of the next section. But for now, I hope you enjoy the video, and I hope you learned something. And I'll see you later.